we continue the lectorium of algebraic graph theory supported by the Mathematical Center in Akademgorodok. Today we are starting a new mini-course consisting of 4 lectures devoted to geometrical topic in the theory of self-similar fractals. The first lecture in this course is titled Convex Halves of Self-Similar Set. It's my pleasure to introduce the lecturer of this course, Professor Andrei Tetenov from Sobolev Institute of Mathematics and Novosibirsk State University.
Hello, everybody. Thank you very much for the honor to give a lecture at this prominent series. So now I begin. The first lecture it will be devoted to convex halves of self-similar sets. Так, видно, да, мой кадр? So first is, what is a convex half? So suppose we have a suppose we have a compact set in Rd, and let H of A or A tilde denote its convex half. What I mean by convex half? A convex half is the union of all simplices with points in the set A. So if A is not contained in a hyperplane, A is a convex body, and its boundary is a hypersurface in Rd. So when we consider the convex sets, we can consider two types of points on its boundary. First type is the points which are contained in some interval, in some segment lying in the set A. And the second type are points which do not belong to the interior of any interval belonging to A. And these points are called extreme points of the set A. We'll denote the set of extreme points by f of A. From basic theorems of convex geometry, follows that the set of extreme points lies in the intersection of A and the boundary of the convex hull of A. And moreover, that the convex hull of A is the convex hull of the set of extreme points of A. For any x on the boundary of A, we can define an outward normal cone, NC. Yes, and along with this outward normal cone, we can define a tangent cone, NT of x at the point x. So if a point x is an extreme point of the convex hull of A, then it cannot belong to any tangent at this point, and therefore it defines special properties of the tangent cone and normal cone. Now proceed to self-similar sets. Our main interest is to define the properties of convex hull of self-similar set. First, I will remind what are the contracting similarities. or the contracting similarities are written in the following form. S of x is R or Q multiplied by x minus y, Q of x minus y plus A. Here, R is a contraction ratio, and it doesn't exceed 1. It's a positive number less than 1. Q is orthonormal linear map. So it's a map which preserves the distances, and A is a fixed point of the map S. So if we have a system of contracting similarities in RD, there is a unique non-empty compact K satisfying the equation K equals the union of images of K under similarities Si. By Hutchinson theorem, this set K is unique, and it is called the attractor of the system S, or in other words, that is also called by a self-similar set with respect to the system S. Self-similar sets possess very interesting structure. We can look. Suppose we have a self-similar set. It is the union of its smaller copies. Each copy is the image of the set K under one of the maps S1, Sn. And these copies are subdivided into smaller subcopies, and it belongs to, it can be, this process may be continued infinitely. So each point belongs to some copy of the first rank, and then it belongs to some copy of the second rank, etc., etc. How to describe all system of these copies and subcopies of different ranks? First, we introduce the set of indices. So these are numbers of the maps defining K. Then, for the copies of the rank n, we consider the set of multi-indices. So these are sequences of indices of length n. And then we define the whole set of all multi-indices, which we denote by I star. And finally, we consider the set of all infinite sequences of indices or addresses for a point. So suppose we have a point in a set K. So to this point, if we have such a point, then we have a copy of the first rank containing this point. Then we have a copy of the second rank containing this point, etc., etc. So for each x, there is a sequence which I show you on this line. So first, all these copies are numbered by multi-indices, and each multi-index defines a map. So if we have I, some multi-index I, which is I1, Im, then Si will be the composition Si1, Sim. So to each multi-index corresponds a unique element of the semigroup generated by the system S. And to each element of the semigroup generated by the system S corresponds a copy of the attractor K. So for each point, there is an infinite sequence of copies, of nested sequence of copies, whose intersection is X because diameters of these copies tend to 0. And the sequence I1, I2, I3 defining this point is called the address of the point, X. So if we have the set of addresses, each address defines unique point, and finally we have the address map of the whole address space to the set K, which is called the address map. So suppose we have a point X with address I1, I2, etc. So if we have the point X has the address I1, I2, I3, etc. And X is P of this sequence, pi of this sequence. But if we take a point with the address, if we truncate the sequence by first symbol and we get the next address, this will be the point x1, and x1 will be the point whose address is I1, I2, etc. And then finally we'll get a sequence. So the point x1 will be the first predecessor of the point x, and this point x2 will be the predecessor of the point 1. So for each point, there is an infinite sequence of its predecessors. Which are defined this way by connected with each one with the other by these maps. Suppose in this sequence of predecessors, some points coincide. This means that the map from second point to the first point fixes this point. So then the address sequence becomes preperiodic, and the point xk is a fixed point of the similarity as ik plus 1 in. Now, let us apply all these things to the convex hulls of self-similar set. So consider a self-similar set and let k tilde or h of k be its convex hull. First, what we need to notice that if you have such a self-similar set, then all extreme points are contained in the attractor, or more exactly in the intersection of the attractor with the boundary of the convex hull. If X is an extreme point, then all its predecessors are also extreme points. Why? Suppose we have some point which is not an extreme point. Suppose some point is inside a segment which lies in the convex hull of K. Then, so it is the convex hull of K, and this is this interval. Then image of this interval will be also an interval lying inside the convex hull of K. And the image of this point will be interior point of some interval, and it will not be an extreme point. Therefore, if you take an extreme point and consider the sequence of its predecessor, all they will be extreme point. What is more interesting? Let us consider what happens with normal cones when we take the predecessors of the points of extreme points. Suppose we have extreme point and take a normal cone at this point. And so it will be the point x, and let x1 be its predecessor. Then x will be si1 of x1 first. And if we consider the polar, or the tangent cone at x1, the image of the tangent cone at x1 will be contained in the tangent cone at the point x. Therefore, the normal cone at the point x will be greater than the image of normal point at the cone at the point x1. Therefore, we have, if you take a normal cone at point x, then normal cone of at x is contained in the image of the normal cone at x1. And qi will be a rotation, because this normal cone will be rotated by the rotation qi. I need to remind you that si1 is ri1 multiplied by qi1, where qi1 is a rotation, and 2x minus ai1 plus ai1. So if we take a normal cone, then it will be rotated by the rotation qi1, but since the normal cone is a cone, all contractions send it to itself. Therefore, we have the image of a normal cone rotates by qi and is transferred to the point x. What is most interesting, if you have two normal cones at different extreme points, then these cones cannot, the interior of these cones intersect in an empty set. Suppose the interior of a normal cone is not empty. If we consider the sequence of predecessors of the point x, then we'll have a sequence of normal cones such that each preceding cone will be greater than initial cone. And all these cones have, if these points are different, their interiors do not intersect. And since the measure of the unit sphere is finite, then the number of such possible predecessors will be finite. It means that at some stage in this sequence of predecessors over of an extreme point, there will be the points in this sequence will repeat, and the map which sends points xk to the points xk plus m to the point xk will be a symmetry of a normal cone at the point xk. So very special case when we consider the fixed point of homotheties. Suppose we have a homothet. Then first, a fixed point of a homothet is an isolated point in the set of extreme points. And the normal cone and tangent cone at the point x is a sharp convex cone. How to check it? So suppose the point x0 is a fixed point of some homothet, and xn is a sequence converging to x0. A sequence of boundary points of the set convex hull which converges to x0. But if we take, so the x0 belongs to convex hull of K, and also it belongs to SI of K, because SI is homothet. So if the point xn is in SI of K, but SI of K is a neighborhood of the point x0, so if the point is in this, xn is in the neighborhood SI of K, then SI minus 1 of xn will also lie on the boundary of K. Therefore, this point will be on a segment connecting x0 and SI minus 1 of xn, and xn is not an extreme point of F. So this shows that all fixed points of homotheties which lie on the boundary and which are extreme points are isolated, and in some of their neighborhood, there are no extreme points at all. Moreover, if you consider the tangent cone, then this tangent cone will be sharp. It means that this tangent cone cannot contain any line, any complete line. All these arguments lead us to the following theorem. If the sorry, there is a mistype. If the semigroup GQ of S, so suppose we have a system of similarities, S1, Sn, S1, Sn, yes, and Q1, Qm will be their orthogonal parts. So we can consider the semigroup generated by Q1, Qm, and this will be a semigroup which will denote by GQ. So if this semigroup is finite, then the set F is finite and K is a finite polytope. It's very surprising because the proof, as you see, is very, very simple. It is extremely simple. So at this place, we need to write, G Q of S. G. If this semigroup is finite, what consider some extreme point X and consider the sequence of its predecessors. So there are rotation. Let us write the rotational parts of maps sending xk to x0. These rotation parts will be q1, q2, q3, and therefore we have considered the composition q1, q12, q123, q3, etc. The number of possible rotations is finite. Then there will be 2 points which will be connected by 0 by I, for which the rotation sending of the map sending xk plus m to k, the rotation part of this map will be identity. And since this rotational part will be identity, then this map will be a homotopy. So in this sequence of predecessors will be some point which will be a fixed point of a homotopy, and this point is an isolated point. And in the set of extreme points of K. Therefore, each of the extreme points will be the image of a homotopy, and therefore image of a fixed point of a homotopy, and therefore it will be isolated point in the set of extreme points. Thus we obtain the result that all the extreme points of K are isolated. And since K is finite, the set of extreme points is also finite, and the convex hull of K will be a finite polytope, which is the convex hull of finite set. We can consider this question from the other side. What is the other side? Suppose convex hull of K is a polytope. Then the predecessor of each vertex will be a will be the vertex, and sequence of predecessors of any vertex will be preperiodic. And this implies that for some point, there will be some point or some boundary point, which is a fixed point of some symmetry of the tangent cone to the polyhedron. But the symmetries, the group of symmetries of polyhedral cone is finite, and some power of this rotation will be identity. Therefore, this point will be a fixed point of some homotopy. So we obtain the following conversion of this group. If K is a finite polytope, then the semigroup GQ of S contains identity. So if the semigroup, if the rotational semigroup of system S does not contain identity, then the convex hull will contain infinite number of sets. Now, this result works for any RD and can be extended to Hilbert space and to Banach space also. Now let us return to plane. So we consider the extreme points for self-similar sets in the plane. So if we have a system of injective contracting similarities in R2, and K is its invariant, and F the set of extreme points of the convex hull of K, we will prove that Hausdorff one-dimensional measure, so length of the set of extreme points, is 0. And moreover, for any positive lambda dimensional Hausdorff measure of F is either 0 or infinity. So let us consider the situation. When we have a convex hull of a self-similar set in plane, that this will be a convex domain in plane, and the boundary of this domain will have a finite length. So this boundary can contain intervals. So there will be boundary segments, which can be called the sides of this convex hull. And the points which are ends of these intervals will be called edge and also these points will be called edges, and these points will be called edge endpoints. So we can consider the set of edge endpoints and denoted by Fe. Because edge endpoints, of course, will be extreme points. the set of edge endpoints. So if we have the set of edge endpoints, this set will be at most countable. Then we can take F and subtract from it the image under semigroup G of S of all edge endpoints, and this difference will be denoted by F. This will be the boundary points, which are first extreme points, and second, which cannot be the edge endpoints. Since we deleted at most countable set from F, this difference will have the same measure and dimension as F. So if we need to say anything about the measure and dimension of the set of extreme point, it's enough to consider the set A. Well, the set A can be, we can make a partition of the set A. Because the set A first of all, the set A is the union of Si of A where is contained, is contained in the union of Si of A when I changes from 1 to n. So these are all maps since K is union of Si of K, right? So A belongs to this union because the predecessor of each point of A is the point of A. But this set may intersect. To avoid this intersection, we will make the following thing. So first we can set S1. We take A1. It will be S1 of A, intersection A. And A2 will be S2 of A, intersection A minus S1 of A. And further we follow by induction, and on the nth step, we'll get this AK will be SK of A intersection A minus union of Si of A from 1 to, oh, union, oh, sorry. Union of AI from 1 to K minus 1. So this way we get a partition of the set K, and then we'll work with this partition. What the sense? So we took a set A and divided it to non-intersecting Borel subsets, and if we take predecessors of the points of A, so each predecessor lies in some of this set. So Sk minus 1 the map Sk minus 1 will send AK to A. And we can define the map psi, which will be defined this way. Psi of x is sk minus 1 of x if x belongs to ak. So we take these sets of AK and they are expanded, all they are expanded, and the union of their images give us again A. So for each point Z0 in A, there is a unique outward unit normal vector. So if we have the set A, for each point of A, there is a unit normal vector, and this map sends A to the unit circle. So what happens with these maps? How to explain this? What happens with this map? So we have that A is union of S K of AK. And these maps, oh, sorry. A, oh, yes. A is union SK. So SK minus 1 sends AK to A. Yes, SK minus 1 sends SK minus 1 of AK. So what happens if we have the set A and this set AK? From one point of view, this map is a expansion, and from the other point of view, if we take the image of it on the unit circle, then it will be a rotation. So this map psi, so we define the map psi, which is sk minus 1 on of x if x is in AK. So we have the equation composition nu and psi on AK is qk minus 1 multiplied by nu on AK for each k. So we have pair of two things. First, we have maps on the convex hull, and second, we have maps on unit circle. So if you take the map AK here, it is expanded and sent to A. It will be sk minus 1. And if we consider the image of this set under the map nu, this image will be rotated by the angle Q alpha. So this interaction between rotations and expanding maps gives us the result of on the Hausdorff measure of the set A. So we prove the following lemma. Let A be a Borel set in R2 and suppose it is partitioned into disjoint Borel subsets, and let psi be a map such that for each I, the restriction of this set on an AI is an expanding similarity. Suppose there are injective mapping nu from A to S1 such that for all I, nu composition psi of x equals qi composition nu of x, when qi is a rotation of a sum to an angle alpha. Then for any lambda, Hausdorff measure of f is either zero or infinity. How can we call this? So if we take, so along with the set A1, AK, we can consider the sets AI1, I2, IK plus 1, which are defined by the following formula. We have the set IK. So if we apply the map psi to A1, AI1, IK, it extends it, it expands it, and we consider the intersection of A1 IK with some AIK plus 1 and get the next set AI1 IK plus 1. So from the partition A1 AK of the set A, we get the next partitions. This will be AI, A1, 1, A1, 2, A, N, yes, etc. So a partitions are corresponding to the set of multi-indices of rank K. And all these partitions will be partition of the set A into disjoint Borel subset. What we should notice, all this set, there are images on the boundary of K may overlap. They can overlap in different ways, but if we take those ones for which the rotation angles are the same, we can consider the new images of these sets of S1, and we'll have that all these sets will be rotated in the same angle. Therefore, if they have the same rotation, so if Q I1 IM is the same for different sequences of indices, then respective images of respective elements of the partition will not intersect. And this will give us the desired result. So consider the family AI when I are multi-indices of the length K. They partition the set A into disjoint Borel subset. So if we look at these sets, So we have that Q I1 IK, the respective rotation, will be rotation in the angle AI1 plus A alpha I2 plus alpha IK. Yes. And if we make any, so if we change the summons of this sum anyway, for each change, the rotation angle will be the same. Therefore, we connect the summons with the same rotation angle in one array. So let be AKN be the set of all unordered arrays of length k consisting of numbers 1. And if we have unordered array, to this unordered array, for example, 1, 2, 2, 3, yes? If we take the sequences of length 3, then it will be 1, 2, 3, 2, 1, 3, 3, 2, 1, and this, since this number 2 is we have it appears here 2 times, then there will be 12 possible combinations of these indices. And this set of all these combinations will be J. So each J will be a family of all ordered arrays of length k consisting of the elements of array A. And this will be all the multi-indices which have the same sum of rotation angles. And so if we take this array J, then we can consider the set of all AI with the same contraction angle. And this set, double KJ, partition the set A. So for each x in WJK, pi multiplied by psi k of x will be q alpha j multiplied by pi of x. So it means that if you take such an array, we can count the number of its elements, and the sum of measures of images of elements under psi k of A will be not greater than the measure of A. Yes? So for each WJK, we have the inequality h lambda of psi k of WJK is less or equal than h lambda of f. Yes, and for all sets AI, the restriction of psi k to the sets AI is an expanding similarity with its ratio not exceeding q minus k. Therefore, h lambda of WJK is less or equal than k lambda of h lambda of A. But the sum of this, since they WJK partition the set A, their sum will be h lambda of M. As a result, we'll get the inequality h lambda of A is less or equal than q to the power of k lambda to h lambda of f multiplied by the number of elements of AKM. Since the set AKM contains less than k to the power of an element, we get that h lambda of A will be less or equal than km multiplied by qk lambda of h lambda of A. And km multiplied by q to the power of k lambda tends to 0 as k grows. As k grows. Therefore, it means that lambda dimensional measure of A may be 0 or infinity. But we know that one-dimensional measure of A is finite. Therefore, one-dimensional measure of A is 0. Therefore, we have the following result. First, for any lambda more than 0, h lambda of f is 0 or infinity. Second, for lambda equal to 1, h1 of f is finite. Therefore, h1 of f is 0. And third, that's all. If we apply the similar technique to the self-similar sets for which the open convex set condition is fulfilled, we can obtain the result that Hausdorff dimension of f is equal to 0. Are there any questions? Okay, good.
Thanks a lot, Andrei.
Thank you.
Thank you, Andrei Tetenov.
Yes.
That's all?
Yes, I think that's enough for the first time.
Uh-huh. Thank you, attention.
So we have two results. First, that if a rotation group in any dimension in the rotation semigroup of a self-similar set is finite, then its convex half is a convex polytope. And second, if we have for any self-similar set on the plane, the convex half, the set of extreme points of the convex half of this set has one-dimensional measure 0. Yes, and the third result, which I will not tell you this day, is that if we have a self-similar set which satisfies open convex set condition, then the extreme set, the set of extreme points of its convex hull, has Hausdorff dimension 0. So these are all results which are known today. And at that moment, I don't know how to estimate the Hausdorff dimension for planes of similar set which do not satisfy convex open set condition. And even if the open set condition is fulfilled, there is a problem. Can we use open set condition for these sets? So there is a lot of open questions in this direction. So thank everyone for your attention. Let us finish the lecture if you have questions.